Hello class, in this lecture video I just want to discuss some of the possible errors that could occur during the process of meiosis, as well as then how we could diagnose those issues as a result of a chromosome number either being too high or too low. So it all starts with a mutation occurring. All right, and again, a mutation is any error or change in a DNA sequence. But we're not really focusing on just one, two, or a couple hundred letters like A's, T's, C's, and G's during meiosis. We're looking at millions of them as a result of chromosomes not separating properly during meiosis. So when whole chromosomes fail to separate properly, it's going to be called a process referred to as non-disjunction. All right, so non-disjunction again is the failure of chromosomes to properly separate during either meiosis 1, so the tetrads or homologous pairs didn't split properly, or meiosis 2, where the individual or leftover sister chromatid pairs do not separate properly. As a result, you're going to get cells, sperm or egg, that are either missing or have extra chromosomes within themselves. So for example, up here in this picture, I should have two cells that each have just 2 chromosomes apiece. But now I have one that has 3 and one that has only 1. So imagine those are 2 sperm cells that now each, no matter what an extra chromosome or missing chromosome, they're going to be abnormal. And if these are one of the 2 sperm that end up fertilizing an egg, a child's going to be born with some type of chromosomal disorder. And some common examples are trisomy 21, all right, which again is Down syndrome, where you have 3 copies of the 21st chromosome, or something referred to as Turner syndrome, where it affects females and they only have 1 X chromosome instead of 2 like they should normally have. So let's say that you're concerned about yourself, family member, or perhaps your unborn child, ladies, having a chromosomal disorder as a result of non-disjunction. What can we do to figure that out? Well, we could do something called a karyotype. All right, and a karyotype is a picture of an individual's chromosomes. All right, and from that picture, you create a chart that you see over here on the right-hand side. Now, I would have took one of your cells, probably most likely from your blood, and I would have looked for a cell that is currently in metaphase of mitosis, because metaphase is the part or the stage where it's going to be the easiest to kind of see all the chromosomes lined up individually down the middle. From there, I could cut them out. All right, so I took a picture under a microscope and pair them up with their homologous chromosomes. You would put the first pair being the largest, and you would just then go in descending size order until you get to the 22nd pair, which should be the smallest. The 23rd pair are your sex chromosomes that are always in the bottom right-hand corner of a karyotype. Now again, the purpose for doing this is there's many reasons, but the main reason is you want to see if a non-disjunction has occurred, and the child is going to have some type of chromosomal abnormality. You could also use it to figure out the sex of a child, but this would be a big waste of time to do, where you could just do something as simple as an ultrasound to figure out the sex. So up here, this is a karyotype of an individual who's normal. You should have 2 chromosomes, all right, which again are normally going to look like X's because we don't really see chromosomes until they've already duplicated. We should only have 2 of them for every type of chromosome. And then a male would be XY. The Y is always very much smaller than the X. And females would be XX. So you wouldn't see a Y chromosome, but you should see 2 X's. So chromosome numbers 1 through 22 up here are referred to as autosomes. Those are the automatic chromosomes that everyone needs to produce everything a body needs. Body parts, tissues, you name it. The 23rd pair, again, is going to be in the bottom right-hand corner, and as I said earlier, those are your sex chromosomes. Males should always have an X and a Y. Can't be a male without a Y. And females should have 2 X's. They shouldn't have 3 X's, they shouldn't have 4, they shouldn't have 1, they should only have 2. Alright, so no matter what the sex of the child is, a normal karyotype should always have a total of 46 chromosomes. Alright, there should only be a pair for every type of chromosome that you would see here. Now, if I wanted to perform a karyotype of an individual, I have to obtain their cells. The best way to do it for someone who is born and living currently is to take a sample of their blood. Alright, from their blood, I could look for cells that were in some stage of mitosis, and take a picture of their cells during metaphase. But if a woman's pregnant and I want to do a karyotype on her unborn child, it's going to be a little harder to get the baby cells. So we're going to do one of two processes. We're going to do what's called either amniocentesis or chorionic villi sampling. I want you to associate both terms with these pictures below as well. So if a woman is several months pregnant, so let's say at least 2 to 3 months, all right, an easy way to do it is you would have to take a large needle and insert that through the woman's abdomen and actually eventually penetrate the amniotic sac that the baby's swimming around in. From there, you would take a sample of the fluid, and in that fluid are going to be skin cells from the baby who are currently living and undergoing mitosis, and you would look for one that's in metaphase. Or if you, or especially your doctor ladies, are very concerned early on that there might be something chromosomally wrong with your child, they could do something, again, called chorionic villi sampling, where they actually have to go through your vaginal canal, through your cervix, and obtain some blood from that placenta barrier right here between the mother and the developing embryo, which, again, doesn't even look like a baby yet, right? So it would take some of that blood, which would have some of the blood from the baby that's mixing and getting filtered here at the point where the mother's blood is, to do the karyotype that way. All right, so again, either one of these would be the way to get a sample of a baby's cell. You're not going to go in with a needle and try to actually poke the baby. That's too dangerous. You can get the fluid. So once you perform a karyotype, you're going to get a picture like this. Again, ignore this MM part. This is just for size reference. So if I look at this right now, I should see 2 chromosomes for every type. Doesn't matter if they're bent or crooked, as long as they look intact. Everything's looking good so far. Everything's looking good so far. So I have 2 chromosomes for numbers 1 through 22 for every type. So there's a total of 44 autosomal chromosomes. Again, 1 through 22 are considered autosomal. But once I get to the sex chromosomes, there is always a place to put a Y chromosome, but there was none, so it's empty. So that's fine. But the problem then is, let's look here. There's only one X. So this would be by default a female, but it's going to be a female who's missing a second X chromosome. All right, that happens to be called something referred to as Turner syndrome. All right, I wouldn't expect you to memorize this name, but again, you should recognize that they're missing an X. Don't tell me that they're just missing a sex chromosome, because are they missing an X or a Y? It's okay not to have a Y, but if it's a girl then, they need to have 2 X's. Here's another example. Again, we go through, we should see 2 chromosomes for every autosomal chromosome. Everything looks good, they look intact. All right, keep going, but I come to the 21st, and there's 3. There should only be 2. The 22nd pair looks okay, and then there is an X and there is a Y. So this is a boy, but they're going to have something referred to as trisomy 21, or common way everyone knows it is Down syndrome. So this individual is a boy who has Down syndrome, and they have a total of, if you count all these, 47 chromosomes instead of just 46. All right, another example here, if we go through and look. All right, there should be only 2 chromosomes for every type. Everything's looking good. Again, they should match up and be similar. All right, I get to the 22nd pair, and there's only 2 for every type, so there's a total of 44 autosomal chromosomes, like there should be. But now I get to the sex chromosomes. There's 2 X's and a Y. So this is going to be a boy. All right, whenever there's a Y, it's a boy, period. But this is going to be a boy who has 2 X chromosomes, which is going to lead to problems as puberty approaches, because you're going to have an extra X that produces too much estrogen, which will counteract the testosterone being made by the Y chromosome. All right, so this would be a boy, but they have 2 X's instead of 1. This happens to be called something referred to as Klinefelter syndrome. And lastly, let's do one more. Again, we're looking. There's only 2. This looks a little weird, but maybe it's just kinked a little bit, so I'm going to ignore that and assume that they're both the same. Looking good for each row. Oh, There's 3 number 18s. There should only be 2. All right, 19 through 22 look good. So there's actually a total of 45 autosomal chromosomes, 1 through 22, instead of 44, because I have an extra 18. If I look at the sex chromosomes, again, it's okay, there's no Y, as long as there are 2 X's, which there are, so this is a girl. But this girl is going to have something referred to as trisomy 18, or otherwise known as Edwards syndrome, which is a horrible condition that we really don't have to get into. But here you can visually see, as a result of the karyotype, that I can anticipate something being wrong with this child that the mother is carrying currently. If you have any questions, make sure you ask in class. Thank you.